Imagine a moment when there was no ticking clock, no sunrise, no yesterday, no waiting. Not darkness, not silence, because even darkness unfolds in time. Even silence has duration. Now imagine something far stranger, a state where the very idea of before makes no sense. A reality where asking, what happened earlier, is like asking, what is north of the North Pole? We are told the universe began 13.8 billion years ago in a tremendous expansion called the Big Bang. But that statement hides a deeper shock. If the Big Bang was the beginning of space and time together, then time did not flow toward it. Time did not prepare for it. Time did not watch it happen. Time may have ignited in that first cosmic event. And if that is true, then the most unsettling question in cosmology is not what caused the Big Bang. It is whether the word before ever applied at all. Tonight, we travel from the familiar ticking of a clock to the edge of modern physics, and perhaps beyond it, to ask a question that shakes the foundation of reality. Did time exist before the Big Bang? Let us begin with something simple. You feel time passing. Your heart beats. You age. Coffee cools. The sun rises and sets. Everything you know unfolds in sequence. One event follows another. Cause precedes effect. Memory points backward. Expectation points forward. Time feels fundamental. But physics has a habit of quietly dismantling what feels obvious. For most of human history, time was considered absolute. According to classical physics, especially in the worldview shaped by Isaac Newton, time flowed uniformly everywhere in the universe. It ticked at the same rate whether you were standing still or racing through space. It was the invisible stage upon which the universe performed. Time existed independently of matter. Even if nothing happened, time would still pass. That view seems natural, even comforting. But in 1905, everything changed. When Einstein introduced special relativity, time stopped being universal. It bent, it stretched, it slowed down depending on motion. Later, in 1915, general relativity revealed something even more radical. Gravity was not just a force acting within space and time, it was the curvature of space-time itself. Space and time fused into a single fabric. Clocks tick differently depending on gravitational strength. Near massive objects, time slows. Satellites orbiting Earth experience measurable time dilation. Without correcting for relativistic effects, GPS would fail within hours. Time was no longer a background stage. It was woven into the structure of the cosmos. Now consider the Big Bang. When we say the Big Bang happened 13.8 billion years ago, we are describing the expansion of space-time itself. Observations of cosmic expansion, beginning with Edwin Hubble, revealed that distant galaxies are receding from us. The farther they are, the faster they move away. This expansion points backward to a state when the observable universe was extraordinarily dense and hot. Evidence accumulated. The cosmic microwave background radiation, discovered by Arno Penzias and Robert Wilson, the abundance of light elements, large-scale structure formation. The Big Bang model became the standard cosmological picture. But here's the subtle part. The Big Bang was not an explosion in space, it was an expansion of space. And because space and time are inseparable in general relativity, extrapolating backward leads to a boundary where densities and temperatures approach infinity, a singularity. In classical general relativity, that singularity represents a limit beyond which the equations break down. At that boundary, time itself reaches zero. Not zero as in earlier than zero, but zero as in the beginning of measurable temporal distance. This idea was formalized in singularity theorems developed by Stephen Hawking and Roger Penrose during the late 1960s. Under reasonable assumptions about energy conditions and gravity, space-time in general relativity appears to be geodesically incomplete in the past. In plain language, the equations imply a beginning. If time began there, asking what happened before becomes physically meaningless within that framework. It's not that something existed in darkness waiting. It is that the coordinate we call time simply does not extend beyond that boundary. Imagine drawing a line that begins at a point. You can move forward along it. You cannot move to a coordinate before the starting point because it's not defined. This is where many scientists say the universe began, and with it, time. But physics is rarely satisfied with singularities. A singularity signals incomplete understanding. It is a place where classical theory fails. Infinity in equations usually means we have pushed a model beyond its domain. General relativity does not include quantum mechanics, and the early universe was unimaginably small and dense, precisely the regime where quantum effects dominate. So to understand whether time truly began, we must look deeper. At scales approaching the Planck length, about 10 to the negative 35 meters, spacetime may not behave smoothly. Quantum gravity, still under development, attempts to unify the geometry of general relativity with quantum principles. One early proposal came from Hawking himself, the no-boundary proposal, developed with James Hartle. In this model, time near the beginning behaves more like a spatial dimension. As one approaches the origin, the distinction between time and space fades. The universe is finite but without a boundary, analogous to the surface of a sphere having no edge. There is no sharp starting point in this picture, no singular moment when time abruptly switches on. Instead, time smoothly emerges from a geometry where the concept of before loses meaning. The analogy often used is the Earth's surface. There is no point south of the South Pole. The question, what is south of the South Pole, is ill-posed. Similarly, asking what happened before the Big Bang might be like asking for a direction that does not exist. But not all cosmologists accept this view. Some models suggest that what we call the Big Bang was not the absolute beginning, but a transition, perhaps from a prior phase. Inflation theory, proposed by Alan Guth in 1980, introduced the idea of a rapid exponential expansion in the early universe. Inflation explains the remarkable uniformity of the cosmic microwave background and the flatness of space. Yet certain versions of inflation imply the possibility of eternal inflation, a process that never completely stops. In that scenario, our observable universe would be one bubble among many, constantly forming in an inflating background. If inflation is eternal into the past, perhaps time stretches infinitely backward. However, the Borde-Guth-Vilenkin theorem suggests that even inflationary models cannot be extended indefinitely into the past under certain conditions. According to this result, any universe that has been on average expanding must have a past boundary. So even inflation may not rescue an eternal past. Other ideas propose cyclic universes, expansions followed by contractions in endless succession. Some versions, such as conformal cyclic cosmology proposed by Penrose, suggest that the remote future of one universe becomes the Big Bang of another through a rescaling of spacetime. In that vision, time never truly begins, it transforms. Still others explore bouncing cosmologies, where a prior contracting phase avoids singularity through quantum gravitational effects, leading to a rebound. In loop quantum cosmology, spacetime is quantized. Instead of a singularity, the universe reaches a minimum volume and then expands again. In that framework, there could have been a before, but not in the classical sense. Time might extend through the bounce, yet its behavior near that regime would differ radically from everyday intuition. Notice what is happening. Each attempt to probe before requires revising our understanding of time itself. This is because time in physics is not just a clock reading, it is a parameter in equations, a coordinate in spacetime, sometimes even an emergent phenomenon. There is another perspective worth considering: thermodynamics. The arrow of time, the reason we remember the past but not the future, is linked to entropy. According to the second law of thermodynamics, entropy tends to increase. The early universe had extremely low entropy relative to its possible maximum. This low entropy beginning sets the direction of time. But why was entropy so low at the beginning? That remains an open question. If the Big Bang represents a state of extraordinary order compared to later cosmic evolution, then time's arrow originates there. Without that boundary condition, the distinction between past and future might blur. Some physicists argue that time may not be fundamental at all. In certain approaches to quantum gravity, such as the Wheeler-DeWitt equation, the fundamental description of the universe lacks an explicit time parameter. The equation describing the quantum state of the universe appears timeless. Time may emerge only when subsystems interact and decohere. In this view, asking about time before the Big Bang might be misguided because time itself is a derived concept, arising from correlations within a deeper timeless structure. This challenges not only cosmology but experience. If time is emergent, then what you feel flowing may not be a basic ingredient of reality. It may be a pattern, a consequence of entanglement and information. The philosopher's question returns: can something come from nothing? But physics reframes it. Perhaps the universe did not emerge from nothing in a temporal sense. Perhaps the concept of nothing without time is incoherent. If time begins at the Big Bang, then causation, which presupposes temporal order, cannot apply prior to it. Cause and effect may themselves be local features within spacetime, not universal principles outside it. This realization shifts the problem dramatically. Instead of asking what caused the Big Bang, we may need to ask whether causality itself is bounded by cosmic history. In quantum cosmology, the universe is not treated as a classical expanding space filled with matter. Instead, the entire cosmos is described by a wave function. This idea was formalized in the Wheeler-DeWitt equation, developed by John Archibald Wheeler and Bryce DeWitt. Strangely, this equation does not contain time in the ordinary sense. There is no variable that plays the role of an external ticking parameter. The equation simply relates configurations of geometry and matter. If the most fundamental equation describing the universe is timeless, then time may not sit at the foundation of reality. It may arise only when we approximate the universe in a certain way, when we separate observer from system, when we divide the cosmos into parts. This leads to a profound possibility. The early universe might not have existed in time at all. Instead, time could have crystallized out of a deeper quantum structure as correlations formed and entropy increased. In this framework, asking what happened before the Big Bang may resemble asking what happened before a wave function collapsed. The language may be misapplied. There's another angle that deepens the puzzle. In classical cosmology, singularities are points where curvature becomes infinite. But many physicists suspect that quantum gravity smooths these infinities. In loop quantum cosmology, spacetime is composed of discrete units like atoms of geometry. Near Planck density, repulsive quantum effects emerge from gravitational quantization itself. Instead of collapsing into an infinite point, the universe reaches a smallest possible volume. Then it rebounds. In such models, the Big Bang is not the absolute beginning. It is a transition from contraction to expansion, a bounce. But the nature of time across that bounce is subtle. Does time reverse direction? Does it pass continuously? Or does it branch? Some calculations suggest that entropy on both sides of the bounce increases away from the central minimum. That would mean two arrows of time pointing in opposite directions from the bounce surface. Observers on one side would see their past as the bounce. Observers on the other side would also see their past as the bounce, but in reverse temporal orientation relative to each other. In that scenario, the universe might be symmetrical across a central moment, with time emerging in two opposite directions. Notice how radically this reshapes the question. The Big Bang would not be the beginning of time, but the midpoint. Now, consider eternal inflation again, but from a more advanced angle. In some models of quantum field theory and curved spacetime, vacuum energy drives exponential expansion. Fluctuations within that inflating background can nucleate bubble universes, each with potentially different physical constants. This leads to the concept of a multiverse. If inflation never completely stops, new universes continue forming. Time within each bubble begins at its local Big Bang, but the inflating background persists. Yet even here, past completeness is problematic. The Borde-Guth-Vilenkin theorem suggests that if the average expansion rate along a geodesic is positive, then that geodesic cannot extend infinitely into the past. There must be a boundary. This does not necessarily imply a classical singularity. It implies incompleteness, a limit to extension. So even in many multiverse models, time may not stretch eternally backward. Let us move deeper still. Some physicists explore the possibility that spacetime itself emerges from entanglement. In certain interpretations of holography, inspired by black hole thermodynamics and later developments in string theory, geometry arises from patterns of quantum information. The holographic principle, originally motivated by insights from Jacob Bekenstein and Stephen Hawking regarding black hole entropy, suggests that the information content of a volume of space can be described by degrees of freedom on its boundary. Later, the ADS-CFT correspondence proposed by Juan Maldacena provided a concrete realization. A gravitational theory in a higher dimensional space can be equivalent to a quantum field theory without gravity on its boundary. In some extensions of these ideas, space-time connectivity itself depends on entanglement structure. When entanglement patterns change, geometry changes. If geometry is emergent, then time, as part of spacetime, may also be emergent. This pushes the origin question into a new domain. Instead of asking when time began, we may ask under what informational conditions time becomes a meaningful parameter. Perhaps in the deepest layer of reality, there is no time, only a network of quantum correlations. What we call temporal flow could be the experience of moving through a particular ordering of entanglement states. Now turn to thermodynamics at a cosmological scale. The second law of thermodynamics states that entropy tends to increase in closed systems. Yet the early universe was remarkably smooth and uniform. Gravitational entropy behaves differently from ordinary thermodynamic entropy. A uniform distribution of matter represents low gravitational entropy because gravity favors clumping. As the universe expands and structures form, stars, galaxies, black holes, gravitational entropy increases. But why was the initial state so smooth? One line of thought suggests that the Big Bang was not a chaotic beginning, but a highly ordered condition. If that is true, then the origin of time's arrow is tied to this special boundary condition. The philosopher's instinct is to ask, why was the boundary so special? Physics does not yet provide a complete answer. There are proposals that inflation dynamically drives the universe toward flatness and homogeneity, but inflation itself requires conditions to start. Some argue that quantum cosmology may assign probabilities to different initial states, with low entropy beginnings being rare but possible. Others suggest anthropic reasoning within a multiverse. Observers can arise only in regions where entropy increases from a low starting point. Still, the fundamental puzzle remains. Let us now confront a deeper conceptual challenge. Time is deeply intertwined with causality. Cause precedes effect. But if time begins at the Big Bang, causality cannot operate before it. There would be no temporal interval within which a cause could act. This forces a reconsideration of the word cause. In everyday reasoning, causes exist earlier than effects. But in certain physical theories, explanations need not be temporal. Boundary conditions can explain phenomena without preceding them in time. Mathematical consistency conditions can determine structures without invoking prior events. For example, in certain approaches to quantum cosmology, the universe's wave function may satisfy global constraints. The entire space-time configuration could be self-consistent without a temporal origin story. This shifts explanation from what happened first to what structures are permitted. Some philosophers describe this as a block universe perspective. In relativity, past, present, and future all coexist within a four-dimensional space-time manifold. Temporal passage is not an objective feature of the equations. It is an aspect of how conscious beings experience slices of space-time. If the block view is correct, then the beginning of time is simply one boundary of the block, not an event that came into being. In that sense, the universe does not start in the way a fire starts. Its earliest moment is simply part of the total structure. But even this view depends on space-time being fundamental. If space-time emerges from something deeper, then the block itself may be derivative. Now consider a speculative but mathematically explored possibility: time as an approximate parameter that breaks down near Planck scales. Just as temperature is meaningful only for large collections of particles and loses meaning for a few atoms, time might be meaningful only for large-scale classical regimes. Near the origin of the universe, the classical notion of time could dissolve into quantum indeterminacy. Some researchers studied timeless path integrals, where histories are not ordered by a single time variable, but exist as configurations contributing to a quantum amplitude. In this picture, what we interpret as temporal succession emerges from interference patterns. This is not merely philosophical, it is embedded in attempts to quantize gravity. Let us examine another frontier: conformal cyclic cosmology. Proposed by Roger Penrose, this model suggests that the remote future of our expanding universe, after all matter decays and black holes evaporate, becomes conformally equivalent to a new Big Bang. When mass disappears and only radiation remains, scale loses meaning. The universe can be mathematically rescaled to resemble a new origin. In that view, there is no first beginning. There is an infinite sequence of eons, each giving rise to the next. Time extends without an absolute starting point, yet each eon experiences its own temporal arrow. Evidence for this model remains debated, including proposed concentric circles in the cosmic microwave background. What matters for our question is that the Big Bang might not be the ultimate boundary. It could be a transitional surface between cosmic epochs. Now shift to string cosmology. In certain string-inspired models, our universe may be a three-dimensional brain embedded in a higher dimensional space. The Big Bang could represent a collision between brains. Time within our brain would begin at that event, but the higher dimensional bulk might possess its own temporal structure. In that case, before would exist in a higher dimensional sense, though not within our observable spacetime. However, such models remain speculative and lack direct empirical confirmation. Step back for a moment. We have explored classical beginnings, quantum bounces, eternal inflation, emergent spacetime, cyclic eons, holographic principles, and higher dimensional scenarios. Each attempt to answer the question reshapes time itself. This suggests something profound. The question, did time exist before the Big Bang, may not have a single answer, because time may not be a single concept. There is thermodynamic time, tied to entropy. There is relativistic time, woven into geometry. There is quantum time, appearing or disappearing in fundamental equations. There is psychological time, emerging from memory and anticipation. To move further, we must confront an uncomfortable idea. The universe may not have evolved in time in its deepest description. What we call evolution could be an emergent ordering that appears only after certain structures stabilize. In canonical quantum gravity, when space-time geometry itself is quantized, the traditional separation between space evolving in time dissolves. Instead of a background clock guiding change, the geometry and matter fields exist in a superposed quantum state. The Wheeler-de Witt equation sets the total Hamiltonian equal to 0. Symbolically, h psi equals 0. 0. No external time parameter driving change. If the universe as a whole satisfies a constraint rather than a dynamical equation in time, then temporality is not fundamental. It arises only when one part of the universe is used to measure change in another part. A physical clock is just a subsystem whose states correlate predictably with other subsystems. Time becomes relational. This relational view traces back conceptually to ideas explored by Carlo Rovelli, who argues that physics does not describe how things evolve in time, but how variables relate to one another. One variable can serve as a clock relative to another, but there is no master clock underlying reality. If this is correct, then near the Big Bang, when no stable subsystems yet existed, there may have been no meaningful relational time. Without distinguishable subsystems to compare, the concept of duration may have no operational definition. Consider what this implies. At extremely high energies, matter and radiation were in thermal equilibrium. Distinctions between particles blurred. Forces may have been unified. If there are no stable structures, no complexity gradients, no information storage, then nothing records earlier versus later. Without memory, can time be said to pass? From a thermodynamic perspective, time's arrow depends on entropy gradients. From a relational quantum perspective, time depends on correlations. From a geometric perspective, time depends on the structure of spacetime. Near the origin, all three may dissolve. Now examine the concept of vacuum. Quantum field theory tells us that what appears empty is not truly nothing. Even in its lowest energy state, a quantum field exhibits fluctuations. Virtual particles momentarily appear and vanish. The vacuum possesses structure, energy, and measurable effects such as the Casimir force. If the early universe emerged from a quantum vacuum state, then nothing already contained laws and potentiality. But even this vacuum presupposes a framework, fields defined over a spacetime or pre-geometric structure. Some proposals attempt to go further, describing a pre-spacetime phase. In group field theory and certain spin network approaches, geometry itself is not fundamental. Instead, combinatorial structures, abstract networks, give rise to spacetime when they condense into a particular phase. In such models, the Big Bang may correspond to a phase transition. Think of water freezing into ice. The crystalline structure emerges from underlying molecular interactions. Before freezing, the structure is different, but the molecules exist. Similarly, before spacetime condensed, there may have been a non-geometric quantum regime. But notice the subtlety. If spacetime condenses, does time exist before condensation? The word "before" implies temporal ordering, yet the phase transition may not occur within time as we understand it. Time itself may emerge as part of the new phase. Thus, language begins to strain. Now turn to another deep issue, the nature of singularities in general relativity. Singularities are not points inside spacetime, they are boundaries of spacetime. They mark the limit beyond which geodesics cannot be extended. The singularity at the Big Bang is not an event located somewhere, it is a breakdown of the manifold description. If singularities signal the failure of classical geometry, then the beginning of time in general relativity may not represent a physical edge, but a theoretical limit. This shifts attention toward quantum corrections. In semi-classical gravity, when quantum fields are placed on a curved background, particle production occurs in expanding universes. Vacuum states defined at one time differ from vacuum states defined later. The very concept of particle depends on the observer's frame. Thus, early universe particle creation is not an event occurring in empty space, but a manifestation of changing geometry. If geometry itself is fluctuating quantum mechanically, the distinction between background and excitation becomes blurred. Now consider causal structure. In relativity, causality is encoded in light cones. Events outside each other's light cones cannot influence one another. The Big Bang is often described as the origin of all light cones. Every event in our observable universe lies within the future light cone of the initial singularity. But if spacetime itself emerges from entanglement patterns, as suggested in some holographic models, then causal structure may arise from information constraints rather than pre-existing geometry. In tensor network models of spacetime emergence, connectivity determines effective geometry. Regions that are highly entangled appear geometrically close. Regions weakly entangled appear distant. If entanglement patterns define geometry, then time ordering might emerge from the way entanglement spreads. This introduces a radical thought. The arrow of time may correspond to the growth of entanglement. Early universe states with minimal entanglement would correspond to low entropy and a definite arrow. As entanglement increases, complexity grows. But entanglement is a property of quantum states, not necessarily tied to a background time. It can be defined abstractly in Hilbert space. Thus, temporal direction might reflect structural asymmetry in the quantum state rather than motion along an external axis. Now push further. There is a theorem in quantum information known as the Page-Wouters mechanism. It shows how time evolution can emerge from a globally stationary quantum state. If the total system is static, subsystems can still exhibit relative evolution when conditioned on correlations with a clock subsystem. In this sense, the universe as a whole may be timeless, while internal observers experience dynamics. If so, asking whether time existed before the Big Bang may confuse internal and external descriptions. From the inside, time begins at the Big Bang because the correlations defining clocks begin there. From a hypothetical outside vantage, if such a perspective is meaningful, the total quantum state may not be embedded in time at all. But is an outside perspective coherent? If the universe includes everything physical, then there is no external time in which it sits. Now consider quantum tunneling proposals for cosmic origins. Some models describe the universe as tunneling from a quantum gravitational state. Tunneling is a probabilistic process usually described in time. Yet in the semi-classical approximation, the amplitude for nucleation can be calculated without referring to prior temporal evolution in the conventional sense. The mathematics resembles barrier penetration in quantum mechanics, but the before is not a classical time region. It is a region in configuration space. Thus, the Big Bang might represent a boundary in configuration space rather than a moment preceded by events. This distinction is subtle but crucial. Configuration space is a mathematical landscape of possible geometries and field configurations. The universe's wave function assigns amplitudes across this landscape. The classical expanding universe corresponds to a particular trajectory through this space. But that trajectory need not be preceded by earlier classical times. It could emerge from a region where classical spacetime is not defined. Now bring in observational constraints. The cosmic microwave background radiation provides a snapshot of the universe about 380,000 years after expansion began. Tiny temperature fluctuations encode information about primordial density perturbations. These perturbations likely originated as quantum fluctuations stretched by inflation. Thus, quantum indeterminacy at microscopic scales became macroscopic structure. If inflation occurred, then microscopic fluctuations were amplified enormously. But inflation itself requires an initial patch with certain properties. Whether inflation can be past eternal remains debated. Even if observational cosmology continues to refine parameters, measuring spectral indices, tensor to scalar ratios, non-Gaussianities, the question of a temporal beginning may remain beyond direct empirical reach. It may depend on which theoretical framework ultimately unifies gravity and quantum mechanics. Now consider a philosophical pivot. Our language assumes linear causation, yet some physical systems are best described by boundary conditions at both ends. In classical mechanics, specifying initial conditions determines future evolution, but mathematically one could equally specify final conditions and derive the past. Some interpretations of quantum mechanics entertain time-symmetric formulations, where boundary conditions in both temporal directions constrain events. If the universe were governed by global consistency conditions rather than initial pushes, the Big Bang might function as one boundary among others. In certain quantum gravity path integral approaches, histories are weighted and summed. The classical spacetime we observe emerges from constructive interference of many possible histories. In that view, the beginning is not a singular event, but a region where the classical approximation becomes valid. Prior to that region, the notion of a definite history dissolves into superposition. The deeper we probe, the more the question transforms. Did time exist before the Big Bang? It may depend on what one means by exist. Exist as a coordinate? Exist as relational change? Exist as entropy gradient? Exist as quantum correlation ordering? Each framework yields a different answer. If spacetime is fundamental and singularity theorems apply, time begins. If quantum gravity replaces singularities with bounces, time may extend through. If spacetime emerges from entanglement, time arises with it. If a universe is described by a timeless wave function, time is internal. If cyclic cosmology holds, time may be periodic or infinite in eons. The question does not merely request a date before 13.8 billion years ago. It demands clarity about the ontology of time itself. And as theoretical physics advances, through attempts at loop quantization, string dualities, holographic correspondences, and quantum information reconstructions, time increasingly appears less like a backdrop and more like a phenomenon that might have conditions of emergence, a phenomenon that might not extend indefinitely backward, a phenomenon that might not even be fundamental.
Then we enter a territory where even the word beginning becomes unstable. In ordinary experience, a beginning is an event preceded by non-existence. A candle begins to burn. A star begins to shine. A human life begins at birth. But in each of these cases, the beginning is embedded in a larger temporal framework. There is always a before in which conditions assembled. If time itself has a boundary, the analogy fails. A temporal beginning is categorically different from an event beginning within time. This distinction becomes sharper when examining the mathematical structure of physical law. Many fundamental equations are time reversal symmetric. The equations governing electromagnetism, classical mechanics, and even much of quantum mechanics do not prefer a direction. If a process is allowed forward in time, its reverse is also allowed. Yet our universe clearly displays temporal asymmetry. The asymmetry seems to arise not from dynamical laws, but from boundary conditions. This suggests that what we call the beginning may be a special boundary, not a dynamical event. In the framework of general relativity, a spacetime manifold can possess boundaries. The Big Bang, in classical solutions, is a past boundary where curvature invariants diverge. But boundaries need not correspond to physical events in the way collisions or explosions do. They mark limits of description. If quantum gravity removes the singularity, then the Big Bang as a literal boundary may dissolve. But even then, there may be a lowest entropy hypersurface, a minimal complexity slice from which entropy increases in both directions. This idea has been explored in certain cosmological models where the universe is time-symmetric globally, but locally asymmetric. Imagine a surface of minimal entropy. On one side, entropy increases in one direction. On the other side, it increases in the opposite direction. Observers on either side perceive their temporal arrow pointing away from that surface. In that scenario, the beginning is not an origin in the sense of non-existence, it is a pivot. Such models challenge the intuition that the universe must have a single temporal arrow extending infinitely into the future from a unique starting point. Now consider the possibility that time may be discrete at the smallest scales. If spacetime has a granular structure, as suggested in certain quantum gravity approaches, then continuity breaks down. Instead of a smooth parameter, time could consist of elementary intervals, perhaps on the order of Planck time, about 5.39 times 10 to the negative 44th seconds. If so, the question of before the first interval becomes ill-defined. There would be no smaller temporal units to reference. However, discreteness alone does not imply a beginning. A discrete sequence can extend infinitely in one direction. The issue is not whether time is continuous or discrete, but whether its domain is finite or unbounded. Now examine another deep idea: scale invariance at high energies. Near the Big Bang, energies approach regimes where classical scales lose meaning. Some approaches propose that at extreme energies, physical laws exhibit conformal symmetry, invariance under rescaling. If scale loses physical significance, distinguishing early from late may also become subtle. In conformal frameworks, what we interpret as a beginning might correspond to a transition between regimes where scale regains physical meaning. This is conceptually related to Penrose's cyclic model, where massless fields dominate in the far future, eliminating meaningful scale distinctions, allowing a conformal mapping to a new Big Bang. Here, before does not vanish, it becomes mathematically transformable into a new phase. Now turn to a different frontier, the intersection of quantum foundations and cosmology. Quantum mechanics introduces indeterminacy. The outcome of certain processes is not determined until measurement, but in cosmology there is no external observer. The universe cannot be measured from outside. This creates tension. Some interpretations of quantum mechanics, such as decoherence theory, explain classical behavior as emerging from interactions between systems and environments. In the early universe, however, everything was tightly coupled. How did classical spacetime emerge from quantum fluctuations? If classical spacetime emerges through decoherence, then the early universe may have existed in a quantum superposition of geometries. In that regime, temporal ordering may not have been sharply defined. Time could exist only as a probabilistic structure within the wave function. Only after decoherence would classical histories separate. This suggests that the very concept of a single well-defined past may be emergent. In path integral formulations, one sums over all possible geometries connecting boundary configurations. The dominant contributions correspond to classical solutions. The beginning, therefore, may represent a region where certain histories dominate, not an ontological edge. Now consider causal sets, a different approach to quantum gravity. In causal set theory, spacetime is fundamentally discrete and ordered by causality. The basic structure is a set of elements with partial order relations representing causal precedence. Geometry emerges from counting relations. In such a framework, time is primary as causal order, but not as a smooth dimension. If the causal set is finite in the past direction, then time begins. If it extends infinitely, then time has no beginning. The theory itself does not automatically dictate which. Thus, the question reduces to properties of the fundamental causal network, yet we lack empirical access to this regime. Now, another perspective comes from thermodynamic equilibrium considerations. A universe that existed infinitely in the past faces the so-called Boltzmann brane problem. In an eternal equilibrium state, random fluctuations would occasionally produce self-aware entities more frequently than structured universes like ours. That raises paradoxes about typicality. To avoid such paradoxes, some argue the universe must have had a low entropy beginning rather than an eternal equilibrium past. This argument does not prove a beginning, but it constrains models of infinite past duration. Now step into metaphysics for a moment, not speculation divorced from physics, but analysis guided by it. If time is emergent, then asking whether it existed before the Big Bang may be similar to asking whether liquidity existed before water molecules formed oceans. Liquidity is a property of many molecules interacting. It does not apply at the level of a single molecule. Similarly, time might not apply at the level of fundamental quantum gravity degrees of freedom. In that case, the correct answer might be, there was no time before the Big Bang because before is meaningful only within the emergent phase. Yet that does not imply non-existence of underlying structure. It implies that temporal language fails at that depth. This reframing avoids a false dichotomy between something existed before and nothing existed before. Instead, it suggests a category shift. Now, consider the possibility that the universe is mathematically necessary rather than temporally caused. Some philosophers and physicists speculate that the laws of physics may be logically constrained such that certain structures must exist. If so, the universe's existence may not require a prior cause in time. In mathematics, objects can be defined without temporal origin. The set of natural numbers does not begin in time, it simply exists within the logical framework. If the universe is analogous to a mathematical structure, its earliest moment may not represent a creation event, but a boundary condition within a self-consistent system. Of course, this idea moves beyond empirically testable physics into interpretive territory, but it illustrates how the question of temporal origin intersects with ontology. Now, return to physics. Observational cosmology continues to test inflation, measure gravitational waves, and probe early universe signatures.
If primordial gravitational waves were detected with specific patterns, they might provide clues about the energy scale of inflation. Yet even precise measurements of inflation would not automatically reveal whether time had a prior phase. The limit lies not only in technology, but in conceptual reach. Because any observation we make occurs within our spacetime, if time has a boundary, signals cannot cross it from an earlier domain. Thus, empirical science may approach but never cross that conceptual horizon. This does not render the question meaningless, it clarifies its scope. We are exploring not an earlier epoch in the ordinary sense, but the conditions under which temporal description becomes valid. To push deeper still, one must examine whether the laws of quantum gravity require global hyperbolicity, a property ensuring predictable evolution from initial data. If global hyperbolicity fails near the origin, classical determinism breaks down. The universe's earliest regime may not support a well-defined Cauchy surface from which evolution unfolds. In such a case, the concept of initial data loses coherence. Instead of a beginning defined by initial conditions, reality may be constrained by global consistency relations across the entire manifold, or pre-manifold structure. This would mean that the earliest moment is not a starting point, but part of a holistic configuration. And within such a configuration, the demand for a prior time may not correspond to any physically meaningful parameter. The deeper the inquiry goes, the clearer one insight becomes. The origin of time is inseparable from the structure of physical law. To know whether time existed before the Big Bang, one must know whether time is fundamental, emergent, relational, discrete, cyclic, bounded, or illusory at the deepest level. And that requires a complete theory uniting quantum mechanics and gravity, something physics continues to pursue but has not yet achieved. So the question remains suspended at the frontier. Not unanswered because it is trivial, unanswered because it touches the root of how reality organizes itself. There is one more layer to uncover before we can step back. When we ask whether time existed before the Big Bang, we are not only asking about physics, we are asking about intelligibility, about whether reality must be explainable in temporal terms. Human reasoning evolved in a world where events follow one another. We understand change through sequence. We assign meaning through memory. Our grammar itself assumes tenses. But physics has repeatedly shown that human intuition is not a reliable guide to fundamental structure. There was a time when motion required a mover, when simultaneity was universal, when space was flat and eternal. Each intuition fell. Time may be next. Consider the possibility that the universe does not require a temporal origin because existence is not an event. In quantum field theory, particles are excitations of fields. The field does not begin each time a particle appears, the excitation does. The underlying structure persists. If spacetime is itself an excitation of a deeper substrate, perhaps informational, perhaps algebraic, then the Big Bang might represent the excitation of geometry, not the creation of ultimate reality. In that picture, asking what came before is like asking what came before a wave formed on the ocean. The ocean was already there, but the wave had a beginning relative to its own structure. Yet we must be careful. Analogies illuminate but do not prove. Now bring attention back to entropy and cosmic evolution. The universe today is filled with structure, galaxies, stars, black holes. Black holes represent enormous entropy concentrations. According to calculations initiated by Jacob Bekenstein and developed further by Stephen Hawking, black holes possess entropy proportional to their horizon area. As the universe ages, matter decays, stars burn out, and the cosmos approaches a thin bath of radiation. In that distant era, time will still pass, but in a universe nearly devoid of structure. Without complexity, temporal experience becomes meaningless. There would be no observers to mark change. If the far future erases meaningful distinctions, and the far past may lack structured time, then the middle era, the era of stars and life, is a narrow window where time feels vivid. This suggests that time, as experienced, depends on complexity gradients. Without complexity, without memory, without irreversible processes, time becomes a coordinate with no experiential weight. Now consider the possibility that the Big Bang was not a beginning, but a transition in a larger cosmological landscape. If spacetime tunnels, bounces, cycles, or condenses, then what we call the origin is a threshold. The mathematics of quantum gravity may eventually describe this threshold not as a singular instant, but as a regime change. In that case, time may not have begun in a sharp flash, but gradually emerged as classical geometry stabilized. Much like temperature emerges when particle numbers become large enough for statistical description. At very small scales, fluctuations dominate. No smooth metric exists. No stable causal order persists, only probabilistic amplitudes. As the universe expands and cools, symmetries break, forces differentiate. Particles acquire mass through mechanisms such as those described by the Higgs field. Structures form. With structure comes distinguishability. With distinguishability comes sequence. With sequence comes time as we understand it. If that story is correct, then time did not exist before the Big Bang in any classical sense, but neither was there absolute nothingness. There was a regime where temporal language had not yet become applicable. This view harmonizes several threads: quantum gravity removing singularities, emergent spacetime from entanglement, thermodynamic arrows arising from low entropy, relational time replacing absolute time. It does not claim certainty. It reflects the direction in which multiple research programs point. Yet an alternative remains possible. Time may extend infinitely backward in some yet unknown framework. The apparent beginning may be a limitation of our models. Just as Newtonian physics seemed complete until relativity expanded it, our current cosmology may be a low-energy approximation hiding deeper continuity. Future theories, perhaps uniting holography, quantum information, and geometry in a new synthesis, could reveal that what we interpret as a boundary is a projection of a more fundamental structure. Science does not close questions prematurely, but what we can say with clarity is this. Within classical general relativity, time begins at the Big Bang. Within several quantum gravity proposals, the singularity dissolves, and time either extends through a bounce or emerges from a deeper timeless structure. Within thermodynamics, the arrow of time originates in a special low-entropy condition near the beginning. Within quantum cosmology, the universe may be described by equations that do not contain time at all. Each framework reframes the question. So did time exist before the Big Bang? If time is fundamental and spacetime has a past boundary, then no. If time is emergent from quantum correlations, then before may not apply. If the cosmos is cyclical or bouncing, then perhaps yes, but not in the way intuition imagines. If the universe is fundamentally timeless, then the question dissolves entirely. The deeper lesson is not merely about cosmology, it is about humility. At the frontier where quantum mechanics meets gravity, our ordinary categories begin to fracture: beginning and before, cause and effect, past and future. These may not be primitive ingredients of reality. They may be features of a particular phase of the cosmos, the phase that allowed stars to shine, planets to form, and consciousness to arise. And here we are, within a narrow window, asking about the edge of time itself. Perhaps that is the most astonishing fact of all. We are temporal beings, investigating the possibility that time has limits. Whether time ignited 13.8 billion years ago, rebounded from a prior contraction, cycles endlessly through eons, or emerges from a deeper timeless quantum foundation, the question drives physics toward deeper unification. To understand the origin of time is to approach the foundation of existence. And at that foundation, we may discover that the universe did not begin in the way stories begin. It may simply be that our story, the one written in stars and entropy, has a first chapter. Beyond it, the language of chapters may no longer apply. And that realization does not close the mystery, it sharpens it.